Hey, what's up? What's up? Pause the screen. You know what to do. Take the agenda. Get that all down. It is Thursday, October 23rd, 2025. As a reminder, we're having a journal check tomorrow. Again, we're having a journal check tomorrow. So just make sure that you are on to that. All right, let's keep it pushing. So this was supposed to say, I saw, I think, I wonder. So we're going to do something a little bit new today or a little bit different. I'm hoping to incorporate this a little bit more as technology is advancing. We see scientific advancing. I just want you guys to think a little bit about things. So we're going to try this out. So this is how it's going to look. You don't have to write anything down right now. It's going to have 3 things that you saw or observed. So I'm going to show you a video. Make sure you observe, pay attention. 2 things that you think about. 2 things that just thoughts that you just had. And then 1 thing that you wonder, like 1 question that you're going to have or that you're curious about. Okay, let's keep it pushing on to the video. Let me get myself up out the way. Go.
When great hunger meets great innovation, there is only 1 robot for the job.
Perfect.
What's going on?
Introducing Dot, your local delivery robot.
All right, so now on to this part. Pause the screen and then fill all this portion out again. Pause the screen. This will be interactivity. Oh, it's number 15. I'm sorry. Number 15. It's interactivity number 15, okay? We'll change that. Cool, got it fixed for you. Okay, so interactivity number 15 again. Pause the screen, get all these things done. Now, 3 things that I saw it driving and being aware of the surroundings. I also saw that I was wondering about the sounds. Like, I saw and observed the sounds, but I'm like, is that really that's gonna sound like? Like, I was curious about that. I was also curious about, like, the talking. Like, is it gonna talk to people? Like that, I saw it talk to people, but so I guess maybe that might be something I thought like, oh, is this thing really gonna talk and have the eyes moving around and interacting with the things around it, or is it just gonna be like driving and like doing the stuff? Another thing I thought was just like, is this going to, and maybe this goes into I wonder, is this gonna take someone's job? Like are like people gonna be put out of places? Another thing I was thinking is how much battery life, how much does it cost? So those are some of the other thoughts that I kind of just had. One thing I just wonder is, I wonder if this will work in every city, because I don't feel like in this part of California it will work that well because it's so spread out. I don't know, so we'll see. So it's just good to wonder and think about the world that's around you, especially as it's evolving with technology being involved. I have cities but no houses. I have mountains but no trees. I have water but no fish. What am I? And hopefully you got this answer. A map. So mountains, waters, cities, but no fish, no trees, no houses either. Yeah, so definitely the answer is a map. I'm curious if you'll leave me some comments in the actual video, because I'm curious to see what did you guys think about what you saw here in this video. All right. Just as a reminder, we're just going to do a short review, and then we're going to move ahead to get everyone's favorite time. Everyone's favorite time. So weight is about how gravity pulls down on stuff. Mass is how much stuff something is actually made out of. Okay? Cool. Now, just as a reminder, motion is when an object moves from one position or location to another. Interacting objects are objects that affect one another. Force is, guess what? Remember, push or pull, a push or a pull. And then Newton's law of action reaction is for every action force, there's an equal and opposite reaction force. Yeah, so that is the things there. Now, let's move it along. Now, net force, we have been calculating this. It's the sum of all the forces acting on an object. So totaling up the total of all the forces that are acting on an object. And Mr. Farr is going to come right down here. And I'm going to do that. And then I'm going to turn on the pen. And then right here, it should be 20 newtons subtract 20 newtons because these are working against each other. So that should end up with 0 newtons. Okay. And then this should be like 20 plus 20. So this would be equal to 40 newtons. And then I'm going to go ahead and say it's in this direction. Okay. And then these are working against each other. And since the largest one is right there, so say 20 minus 16 is equal to 4 newtons. And it's going to be heading in that direction. And will there be motion here? Yes, because the forces are unbalanced. Will there be motion here? Yes, because the forces are also unbalanced. And then will there be motion here? The answer is no. There will be no motion. Now, the reason I'm saying this is because we are having a quiz next week, and these are the kind of things you have to answer. Is it unbalanced? Is there going to be motion? And then what direction will that motion be in? And then you can tell me the strength of the force that's moving in that direction. So all of those things you can find from this diagram right here. Okay, let's keep it pushing on to the next set of note-taking time. All right, yes, you need to draw the car, so handle that. Acceleration. So acceleration is a change in velocity or speed, direction, or both. So yes, draw the car. So increasing speed or decreasing speed. A lot of times we like to only think of increasing speed as acceleration, but any change in speed is technically acceleration. So also when you change direction, and if you think about changing directions, oftentimes when an object changes direction, it actually has to decrease speed. That's very typical of what is happening there. So increasing speed, decreasing speed, or change in direction, all three of those are acceleration. And yes, draw the examples. I want to see your amazing car drawings. Pause the screen if you need it. Mr. Farr is going to keep moving forward. Okay. Boom. Okay, so direction. Direction is a straight path that an object can move along. Again, direction is a straight path that an object can move along. Typically, when we talk about directions, we're talking about as it pertains to the Earth, north, south, east, west, and we kind of coordinate that off the north and south poles of the actual Earth. And I asked some students to point in the direction that was north, and we got people pointing in 2 different directions. So that's better than all 4 directions. We'll see as we go out throughout the day. I'll keep asking and we'll see how the answers will look. We'll talk about that. How do you determine what direction is which, right? Like just from a very natural standpoint, how can you figure that out? So a straight path. So again, direction is a straight path that an object can move along. Okay. Cool. And we are on to the last note of the day. So that should make y'all happy. It's also the largest note of the day. So Newton's second law is acceleration of an object is directly proportional to the net force and inversely proportional to its mass. So if you look here, and I'm going to try and sum this up in as simple as a way as possible. I'm going to turn this off. It's this. When force goes up, acceleration goes up. So the more force that I apply here, then the more the acceleration of the object goes up, right? However, if I right, let's just say I have this ball and I use this amount of force, right? Acceleration will go up. However, if the mass of the object goes up, right, and I use the same force, then acceleration typically will go down because you're going to need more force to get an object with more mass to accelerate. So we're going to put this formula down here. We will learn how to use that, so don't trip out, okay? So get all these things in there, and guess what? We will talk more about this over the next week so that you can kind of get this in your brain. Now also, free body diagrams is equal to, are the diagrams that show all the forces acting on an object. I'm just now giving you a name to the thing that we actually were already doing. We were already drawing and working with free body diagrams. That's what you guys did in your last lab. and you were already making diagrams showing the forces that were acting on them. Now we just have a name for them. So get all these things in there. Now over here on this formula, I do want to put this out here. This F is equal to the net force, okay? It is equal to mass times acceleration. So force is equal to mass times acceleration. So whatever the mass of the object is and how much it's accelerating or its speed, that is going to be equal to force. Okay, so and we will talk about how to use the force formula. Don't trip out. Just get everything written down, and then we will go over it over the next week, and then you'll be very comfortable with it. Not a big deal. Okay, cool. The last thing I did just want to show you guys is you know what, we will look at this today. I don't know if we'll have time. I think, yeah, I'll show it to you guys in this video so you guys just get some examples.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
We're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force being our bungee cord here. We'll put it on our bungee, and we'll pull it back. And you can see how fast it accelerates because there's very little mass. Next we'll try a little spaceship. A little more massive, and you can feel it because as you move it, you can feel it, the kind of force, the extra force you have to push with your hand.
Yeah.
So we'll put our spaceship on our launcher here, same spot.
Much slower.
Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Go back the same amount on the force, and here we go.
Ooh, very slow.
Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
All right, so that was just a demonstration just showing that even though the same amount of force was applied each time, right, as the objects became more massive, their acceleration went down. And that's exactly what we wrote down. That's exactly what we wrote down in the notes to say that, hey, as we see the mass increasing of the object, then we will see its acceleration go down. But if there's more force applied, then we will see the acceleration go up, right? So that is everything. We do have one other assignment that if you can start, but I do want to say we have 2 weeks to go. You can start. It's on pages 65 and 67. I know. And it is the changes in force, linking, literacy. So we'll have time to work on this tomorrow and finish. It is due tomorrow. All right, y'all. Peace.